In the previous video, we demonstrated uniform circular motion. Now in this video, we'll explore how to use our ElectroPhy module for UltraEdge detection, just like in cricket, where it's used to determine if the ball has touched the bat. In professional cricket, microphones in the stumps pick up sound to detect contact between the bat and ball. But we're taking a different approach. With our ElectroPhy module, we can detect even the smallest vibrations, like a light tap of my finger on the table, and it shows up on the waveform. Now, let's attach the module to the back of the bat. I'm heading to the field to test this out. I've invited some of my college mates for a game of cricket after a long time. Everything is set. Let's turn on the module. It's connected to our receiver software, where we'll monitor the waveforms. We'll be plotting the resultant acceleration, which is the square root of the sum of the squares of the accelerations along all three axes, minus the effect of gravity. One challenge we've encountered is that the waveform changes even when the ball doesn't make contact with the bat. We need to filter the signals so that only bat-ball contact is highlighted. Here's the plan. First, we'll observe the waveform when the bat moves without hitting the ball. Then, we'll observe the waveform when the bat does make contact with the ball. Then, we'll analyze the frequency domain plot, FFT, for both conditions. Lastly, with this information, we'll design a digital filter that only shows changes when the ball touches the bat, filtering out other movements. Let's begin by comparing the first two test conditions side by side. On the left, the bat is moving without contact, and on the right, I'm gently hitting the ball. You can clearly see a sharp spike when the ball touches the bat, indicating a high-frequency signal. We can conclude that bat-ball contact generates high-frequency vibrations, while other movements produce lower frequencies. This means we need to design a high-pass filter to isolate the bat-ball contact. To determine the cutoff frequency, we need to plot the FFT of both conditions. On the left, we have the FFT when the ball doesn't touch the bat, and on the right, when it does. Based on these plots, we'll set the cutoff frequency at 100 Hz and design our high-pass filter. Now let's look at how the high-pass filter is implemented in the Python code. The sampling frequency is 1 kHz and the cutoff frequency is 100 Hz. The filter order is set to 15. This gives us the frequency response of the high-pass filter. More advanced filtering would be needed to remove signals from the bat hitting the ground, but for now, we'll keep it simple. It's time for the final test. As you can see, bat movements are completely filtered out. Now I'm gently touching the ball with the edge of the bat and the signal is clearly visible. The filter is working. Now I'm playing a real game, carefully trying to edge the ball. Here's a ball that lightly touched the bat and the keeper caught it. Let's check the replay in slow motion. Yes, our UltraEdge detection worked perfectly. You can see the sharp spike. In this next delivery, only I felt the vibrations, and no one, not even the keeper, realized there was an edge. Let's zoom the waveform and review it in slow motion. And there it is. Small vibrations, but clear evidence of the edge. ElectroPhy has successfully detected an edge that's invisible to the naked eye and inaudible to the human ear. That's it for this video. If you enjoyed it, leave a comment below with your thoughts or ideas for future experiments using the ElectroPhy device. See you in the next one.